Guys, sorry about that. We had a couple visitors just kind of stop by. So we would get 0.9 equals 1 minus e to the negative t over tau. So I could simplify this a little bit further if I subtract 1 from both sides. If I do that, I'll get a negative 0.1 on this side, and I'll have a negative e over here. So it's really like I could just say the negatives would be both positives then on both sides. So I'd get 0.100 equals e to the negative t over tau. Okay, so I know that natural log of e is 1. So if I take the natural log then of both sides, then that would help me simplify. Natural log of 0.100 is going to be equal to a negative time over tau. If I take the natural log of 0.100, we should get, go over here, a negative 2.30. So if we take that natural log of 0.100, we get a negative 2.3, and that's equal to a negative t over tau. Well, my goal is to find t, and we have tau, so really then this would just become a negative 2.30 times that time constant tau, which is 5.10 times 10 to the negative third. So if I multiply then negative 2.30 times my constant, my time constant, 5.10 times 10 to the negative third, I'm going to end up getting my time to be equal to 11.7 times 10 to the negative third seconds, which would be 11.7 milliseconds. Okay, so we found our time, we found our time constant. So if we kind of go back to this problem here for a second, this says that we dropped this small sphere and it has a mass of about 2 grams. So we can think about that as like being a marble. We're dropping this like marble-sized sphere into a vessel of oil, and we know it's going to experience some resistive force, and it says that it's going to be proportional to its speed in this case. We wanted to determine the time which the sphere is going to reach 90% of its terminal speed. So it does that in 11.7 milliseconds. So that marble is, that's a fairly quick time interval for that sphere to reach 90% of its terminal speed. So because of this, because of that short time, it's probably like we're not even seeing almost this resistive force at all. It would be difficult, I think, for us to catch that. So short time interval, it may be hard for us to see maybe macroscopically that happening. Okay. So we're almost done, guys. We also, in section 6.4, the last thing that we need to talk about is that second type of resistive force, and that's when that resistive force is proportional to v squared. So typically this is when objects are moving at high speeds, or we're thinking about like really large objects. So for example here, we may be talking about like a baseball, because baseballs can move at really high speeds. We may be talking about a skydiver, we may be talking about a car or an airplane, but in those cases is when we would have resistive force being proportional to v squared. So we have an equation, again, for resistive force in terms of speed, and that's going to be R equals 1/2 d times R times A times v squared. Oh my gosh, what do all of those things mean? Okay, so we know R is just our resistive force. D is what we're going to call the drag coefficient. So it's just a dimensionless constant, just an empirical quantity, and it's just going to be the drag coefficient. That's what we're calling D. R is going to be density of air. A is going to be the cross-sectional area of the object, and a V is going to be our speed of the object. Okay, so let's say, for example, we have an object that's falling through air, and now we're going to have to start accounting for air resistance. So I'm going to have a resistive force here. I know that at first, as it is moving down through the air, this R, my resistive force, is going to start increasing. And once my resistive force is equivalent then to my weight force, we know that's when we've reached that terminal speed. If I'm thinking about just this first part right here. As it's beginning to fall through air, we're accounting for air resistance. So I want to think about the sum of the forces in the y direction. So the sum of the forces in the y direction would again be my weight force, so mg, minus my resistive force, which would be that 1/2 my drag coefficient, my density of air, the cross-sectional area of the object, and then the speed. And since it's falling through the air, that resistive force is increasing, I see that these two vectors are not equal, must be accelerating. So it's going to have some net force here. So that's going to be equal to mass times acceleration. So just like we did in the last one, where resistive force was proportional to v, we came up with an equation or an expression for acceleration. Guys, we just did the exact same thing here. So when I'm rearranging this to solve for acceleration, I'm going to get my acceleration is equal to g minus d. That is density is a Greek symbol, rho. So I have my drag coefficient times the density times cross-sectional area over 2 times mass, and that whole thing would be times that speed, which is squared. Okay, so the terminal speed, we know, is going to occur when acceleration goes to 0. If I set my acceleration then here equal to 0, then we can rearrange this equation to solve then for that terminal speed, and that's going to give me the square root of 2mg over my drag coefficient times density times that cross-sectional area. Guys, since I just showed you how to do it for the last one, I'm going to expect that you can do this for the same thing. But don't be surprised if I give you maybe this picture, just this free body diagram. I'd want you to write this. I'd want you to solve for acceleration. And then if I were to tell you, write an expression for the terminal speed, you should be able then to know that acceleration is going to go to 0 when terminal speed occurs, because that resistive force now is in equilibrium with that weight force. So acceleration would be 0. I would set a equal to 0 in that last equation, solve for terminal speed, and I would get this. So you should be able to do something like that. So let's do an example of this one. This says a pitcher hurls a 0.145 kilogram baseball past a batter at 40.2 meters per second. We want to find the resistive force acting on the ball at this speed if terminal speed is 43 meters per second. So we want to find R. That's our goal. Let's find R. Okay, so in this problem, let's first talk about all of the things that they gave us. Let's talk about these things. So we know, let's go back to it, guys. Mass. We know mass is 0.145 kilograms. Let's write that down. Mass is equal to 0.145 kilograms. Okay, what else do I know? I also know that, well, we know acceleration due to gravity, g, is going to be 9.80 meters per second squared. I also know that the terminal speed, we were given that, vt, is going to be equal to, that was 43 meters per second. And then they also gave us a speed. They gave us this initial speed then of like that 40.2. So we know that this pitcher is hurling this baseball past a batter, and once it's past that batter, we know that it has a speed of 40.2. We knew that its terminal speed was 43. So I just know that at another time, we know that v is equal to 40.2 meters per second. So we know all of these things. Our goal is to find R. Let's find R. What's the resistive force? Okay, well, we can find, like we said, resistive force. We have an equation for that. And that is when R equals R 1/2 d rho a v squared. Okay, well, we have some problems here because we don't know cross-sectional area. They didn't give us A. We don't know what the drag coefficient is here either. We could look up the density of air, because we can maybe hopefully assume that since it'd be traveling through air,